А что, мы заставочку не будем ставить, Ром?
Сейчас поставим. Сейчас, секунду.
Угу, отлично.
Так, мы в эфире, можно начинать.
Отлично, коллеги, всем добрый вечер. Начинаем наш очередной семинар в Центре когнитивного моделирования. Переключаемся на задачи обучения с подкреплением. У нас сегодня выступает наш сотрудник Адитya Нарендра, и мы будем говорить про мультизадачное обучение с подкреплением. В робототехнике это достаточно важная задача, когда мы, например, с манипулятором робототехническим работаем на столе, хоть и с полностью наблюдаемой средой, но с разными объектами. И оказывается, что хотелось бы выучить такую стратегию, не дообучая ее, не добавляя каких-то новых демонстраций, например, и чтобы она умела работать с разными объектами. Таким образом, мы получаем такую мультитаск-задачу с разными типами вознаграждений. И как раз об этом Адитя сегодня и поговорит, и также сделает упор на то, как можно использовать model-based подходы в этом случае. Адитя, тебе слово.
So, hello everyone. I'm Aditya Narendra. I'm a fourth course student at FISTech and I also work in Center for Cognitive Modeling Lab. And today I'll be presenting the seminar on the topic leveraging single and multitask reinforcement learning for Mobile-Aloha robot. The presentation would be in English, unfortunately, but hopefully in the next seminar I'll present in Russian. So let's start. First of all, what exactly is Mobile-Aloha robot? It's basically a multi-control mobile manipulator robot developed by the researchers at Stanford and Google DeepMind. So it is a bimanual robot, so it has two robotic arms which allow it to perform manipulation tasks at a very human level. At the same time, it has a mobile base. So it is able to perform some manipulation tasks and also navigation tasks very easily. And combining both the manipulation and the navigation capabilities, uh, uh, it is able to do some mobile manipulation tasks, for example, picking up an object from one corner of the room and placing it at the other corner. And due to all these features, it has been regarded as one of the best robot of its kind, and specifically due to the fact that it is really cost effective, and at the same time, it can be used for in a household environment, and this can be done very efficiently. So these are all like the features of the robot itself. Now coming to the technicalities, it has 2 degree of freedom for its base. So it has single degree of freedom for each wheel. Now, secondly, it has two effective manipulators, and each manipulator has 8 degree of freedoms and so in total, it has 16 degree of freedom for the entire manipulation stack. Right now, the researchers are using ACT, which is chunking with transformers, and it's a type of behavior cloning or imitation learning algorithm. And honestly, as you can see from the video, the results have been pretty great. The the tasks are being done by the robot. They are very complicated tasks, and the robot is able to do these tasks very effectively, and the policy seems to be very robust. So everything seems great. So what exactly if is our aim if everything is working so perfectly? So as I was saying, like everything is so great, but of course there is some downside to every algorithm in this world. There is not a single general algorithm which can be used in all the cases. And ACT itself has some downfalls, and we'll discuss that now. So first of all, imitation learning in general relies heavily on expert data. And in case of Mobile-Aloha, this data is being collected in form through teleoperations or through some heavy simulation. And this entire process, it can be really time-taking. It can be really inefficient in some manner. And this is a big problem. Secondly, the entire policy of imitation learning, it relies very heavily on the expert data itself. So the quality of the data is the main thing that defines how good the policy would be. And of course, like for any kind of ML or algorithm, the data is important, but like these challenges can be tackled in, for example, reinforcement learning, but in case of imitation learning, it's very difficult to fix this problem. And finally, imitation learning is not as easily generalizable because, of course, it's just based on the architecture of the algorithm itself, because the agent is not able to do a lot of exploration when it's learning the policy, because it's learning the policy through the data and it doesn't do an exploration of its own. Unlike, for example, reinforcement learning algorithms, specifically online reinforcement learning, where the agent learns some policy through the use of exploration or active exploration, either via simulation or in real environment. And all these problems can be really big in case of Mobile-Aloha, which is supposed to work in a household environment among humans. And this environment can be pretty dynamic, because you can imagine yourself if you have a robot in your house and you are constantly moving around it, and the robot is supposed to do its own job, and this can be like a big problem. So all these are really big drawbacks of imitation learning, and we want to solve this problem through the use of reinforcement learning, or specifically multitask reinforcement learning. So coming to the mathematical part of our research, we formalize our problem in a form of MDP, which is Markov decision process, and it's a very general formulation for any type of reinforcement learning environment. So the idea behind it is that we need to maximize the discounted reward over some period of time. So here we have the reward function. The reward function takes in the state at time step t. It takes in the action that the agent is doing, and it takes in the next step. Like given the action, we get some another state, and this reward function also takes in this state as an input. And then we multiply this reward function by the discounted discount factor. And discount factor is basically used so that the current reward would be more valuable as compared to the reward that we got, maybe the reward that we will get maybe down the line. So this is a very simple formulation of our problem statement, and this is the general formulation of MDP. Now we choose some baseline algorithms, and first of all we have PPO. It is developed by, I think, OpenAI, and it's a single task algorithm. Single task means that effectively a PPO agent can be trained to do only one task. We can try to train a single agent to do multiple tasks. So for example, we can train it to do a task of picking a cube, and PPO agent can effectively do that. But if we try to train the same agent for placing the cube task, then the result might not be as good. So this is called a single task algorithm, and PPO is an example of that. And secondly, it's on policy. So on policy means that currently, if the agent is learning a policy, it uses the current learned action for choosing the next action. So it already knows some policy, it already has some idea about what action it should take next. And this is basically the policy that PPO chooses to guess the next optimal action. So that's our first baseline algorithm. Second is SAC, or SS, or soft actor critic. It's also a state-of-the-art baseline, and it's also single task like PPO, but this is off policy. So it means there is more active exploration in the part of the agent, and the agent is not using its current learned policy to choose the next set of action. And this can be really good if you want some very good exploration, but at the same time, it has its downfall because it can lead to not so robust policy, especially if you are using a vectorized environment. So we have multiple environments and a single agent is learning in the entire thing. So there is SARC, and finally we have Dreamer v3. Now, Dreamer v3 is a multitask reinforcement learning algorithm. This means that we can take a Dreamer v3 agent and we can train it to do a picking task. And then we can train the same agent to do the placing task. And ideally, the agent should be able to learn both of the tasks effectively. So this is Dreamer v3, and this is also off policy like SARC. And when Dreamer v3 first came out, it was regarded as one of the best multitask algorithms, mostly because it had some groundbreaking breaking scores in benchmarking, especially in Minecraft environment. Dreamer v3 is the first algorithm to be able to mine diamonds in Minecraft. So it was really groundbreaking for its time. And fourth, we have TDMPC2. It's also known as Temporal Difference Model Predictive Control 2 because it's based on TDMPC1. And this is also multitask and it's also off policy. And this would be the focus of our research. This algorithm is the one that we are mostly interested in, and we will talk about it in more details a bit later. And finally, we have two legacy algorithms, FQL and DFQL. And these algorithms, when they first came out, they were really the baselines for the highly dynamic, high action space environments. But they are legacy algorithms, so they're a bit old. They are not as complex as, for example, PPO, TDMPC2, etc. So let's talk a bit more about TDMPC2 because it's very new algorithm. It's not as popular, but it's really promising. So the entire architecture of TDMPC2 is based on neural networks. So first of all, we have the encoder. Encoder basically takes in the state, the raw data from the, for example, sensors, and then it encodes this into a state that could be understood by the TDMPC2. It encodes this raw information from the environment into a latent state. Second, we have latent dynamics. So this is also a neural network, like the entire part of the architecture. And latent dynamics basically takes in an action and it takes in the latent state that we get from the encoder and it tries to predict the next state. And third, we have the reward. This is just the basic neural network which tries to predict the next reward given some action and a state. And then we have terminal value. Terminal value is a very similar neural network to the reward neural network, but here, this instead of predicting the next reward, it tries to predict the cumulative reward over a certain horizon. So maybe from time step t to time step t plus n. And finally, we have policy prior, which is basically the neural network which predicts the next optimal action. Now, from the picture, you can see we get the state from the environment, then it's being encoded into a latent state in form of Z1. And then from there, the agent predicts the action, the reward, and the terminal value. And then we take that action, and then we get the next state, and then the process is repeated over and over again until the policy is robust. And here is the policy prior for TDMPC. This is, for example, earlier in the slides, we saw the MDP, and this is the more specific form of MDP for TDMPC. So here we have the same maximization of the discounted reward over time. And here we try to basically converge this policy into a normal distribution where the mean is the robustness of the policy and the standard deviation is basically how confident the agent is about the policy that it's learning. So the idea is to find a balance between the two because we need a robust policy, but at the same time, the agent needs to do more active exploration so that the policy is more generalizable, for example. So let's talk about our experiments. We have two parts for our experiments. First, we simulate the experiments in Mujoko. Mujoko is a very popular simulation environment for reinforcement learning in general, and that's our first choice. And basically, for Mujoko, we have the simulator and we get some information from the simulator. So the observation and the state, etc. Then these information, it's being wrapped the into a format which can be understood by TDMPC2, which is the agent. And this is a very crucial step because if we don't encode the observation from the environment properly, if we don't wrap the environment properly, it can be problematic for the agent, and maybe the agent won't be able to learn things very effectively. So we have to develop our own custom wrapper for our tasks. And then this wrapper gives the encoded observation to the agent. And then the agent performs some task, tries to learn the policy, and then gives out the action. And then we take this action, we give it back to the wrapper decodes this action, and then sends it to the Mujoko simulator. And the action is performed. And once the action is performed, we get the next state, we get some reward, etc. And we repeat the process. So this is how the entire simulation architecture works here. And for our experiments, we chose three tasks which are relevant to Mobile-Aloha itself. The first task is navigation. It is a simpler task, as you can see from the action dimension, because it has two action dimension, which is the same as the number of freedom for the base. And here we have 16 dimensions for observation. And basically, the task here is that the robot needs to maneuver around some obstacle and reach a terminal position that is being randomized. And we'll talk about the tasks once more in the next slides. Second, we have manipulation, and this is a more complicated task. It has 7 action dimension, which is the same as the number of degree of freedom for a single manipulator. And for the sake of simplicity, we use the single manipulation, not by manual tasks. And also we don't use visual observation. Instead, we just use the simple state-based observation because the goal of our research is to compare the algorithms, not to see how well they perform in some specific environment, all that. So here we have that. And finally, we have the pick and place task. And pick and place task is basically a combination of navigation and manipulation tasks. And next, we will learn more about the task itself. So first, let's discuss how the controls work. So first of all, we have the base control. And here we take in the angular velocity and the linear velocity of the wheels, and then we get some torque in return, and we have to basically clip these actions that are being performed by the agent so that we have a minimum value and a maximum value. And we have to make sure that the predicted action doesn't like break these constraints, or else the simulation might break and it could be a big problem. So this is a very simple controller algorithm for the base. And next we have the controller for the Mobile-Aloha robot itself. It uses OSC, which is Operational Space Controller. And this is a very general algorithm for manipulation, where we get the end effect, where we basically give the end effector position and the orientation that we want to the OSC, and then it predicts some joint effort or torque for each of the joints that we have in the manipulator. So next we have the tasks that we want to discuss. First of all, we have the navigation task. The reward function is very simple. We have the negative of the distance between the robot and the target. So this is negative because as soon as the robot starts moving closer to the target, the reward becomes less and less negative. And next we have some bonus in form of an indicator function. So if the robot reaches the target, then we have an additional bonus for it. And then we have a negative penalty in case there is a collision with the obstacles. So in the picture, you can see that there are two obstacles here visually, but we had more obstacles. So this is the reward function, and also the entire simulation is randomized. So in each episode, we have a different terminal position that we want for the robot. So this allows for more active exploration. Next, we have the manipulation task. The reward function is also pretty similar to the navigation reward. So here we also have the negative of the distance between the robot and the cube, but here the distance is of the end effector, so the manipulator of the robot. And as the manipulator goes closer to the object, the distance becomes less, so the reward becomes less negative. And then we have some additional bonus if the cube is picked up. And then we give some more bonus if the cube is reached a certain height. And this threshold height for us was 0.4 meters. And finally, we have mobile manipulation. Mobile manipulation, as I said earlier, is the combination of the navigation task and the manipulation task. So first of all, the robot is supposed to pick up the object. And once the object is picked up, the robot needs to place the object at a different position. And even the reward itself, it's a combination of the navigation and the manipulation reward, as you can see. So let's see the results that we have for our experiments. First of all, we have the navigation result, and you can see here, first we have the blue line, which is PPO. And for navigation task, which is very simple, it's low action space, PPO performs really well. But as soon as the task becomes more complicated, so in manipulation task, you can see that the results are not as good. And in the mobile manipulation task, it's good, but I mean, it's not as good, but it's not too bad. Next, we have SOC, and SOC is the gray line, and you can see that SOC performs worse than PPO for the simple navigation task. But as soon as the complexity increases in manipulation task, the SOC is better. And this is unknown behavior of SOC, that it doesn't perform as well in navigation tasks compared to PPO. And then when we have mobile manipulation tasks, SOC initially performs well, but then its performance is worse. And third, we have Dreamer V3, which basically fails to converge for the higher dimensional tasks. So for example, for mobile manipulation and manipulation, but for navigation, it's fine. And this might be due to the fact that Dreamer V3 itself is very overly optimized for benchmarking environments like Atari or DM Control, etc. And as soon as we use it in a custom environment, its performance is not as good. And this is a known problem, and even in the original DDMPC2 paper, the authors faced a similar problem with Dreamer V3. Next, we have FQL and DFQL, and as I said earlier, they are legacy algorithms, and at one point they were really well, but eventually, after so long, they are not as complicated environments, and thus they don't perform as well as the advanced algorithms like PPO, etc. And finally, we have TDMPC2, which is the spotlight algorithm for us. And you can see for the navigation task, TDMPC2 performed really well, and it has the same level of performance as PPO. But then we have the manipulation task, and you can see that TDMPC2 is still consistent, even though the task is more complicated. PPO doesn't have as good of a performance, but TDMPC2 is still performing well. And in the mobile manipulation task, we can see the performance is not as consistent, but still it is able to reach a certain threshold. And this is really impressive because this was all done without any hyperparameter tuning or anything. This is just, this is really impressive for an algorithm to be so generalized. And next we compared single task and multitask TDMPC2 agents. So the single task agent was trained on individual tasks. So we had one agent which was trained on picking, one agent which was trained on navigation, and then one agent which was trained on mobile manipulation. And then we trained a general multi-agent, multitask TDMPC2 agent. So we took one agent and then we trained it for all three tasks. And then we compared the results. And you can see after 3 million interactions for training and 1 million interactions for evaluation, uh, we have the normalized success rate. And of course, it's obvious that single agent TDMPC2 would perform well, it would outperform the multitask agent, but the multitask agent is not lagging very much behind. And this is really impressive because there are no other algorithms out there which can basically compete with the single task agents. And this is really promising results from TDMPC2. Now we choose the next set of simulators, which is Isaac Sim. It is developed by NVIDIA. And it is a more complex simulator because it has more realistic physics, it has more realistic actions, etc. And we chose two different approaches for it. And first of all, we only have manipulation task for it. So we have first task is just picking up a cube, second is placing, and third is picking and placing simultaneously. And we chose two approach. First, we took just the manipulator of Mobile-Aloha, as you can see in the left image, and we trained an agent on that. And then we chose the entire Aloha and we trained an agent on that. And we have two different results for it. So you can see the manipulation tasks that we have. So we have the picking task and we have two type of picking tasks. First one is just with the manipulator, and the Aloha is supposed to pick up an apple, which is a realistic object. And the second, we have the picking task with the entire Mobile-Aloha robot. And third, we have the placing tasks as you can see, the manipulator is, it already contains it is already holding the object, and then it needs to place the object at a certain position. So these are the four tasks that we decided to go with because they are relevant for Aloha itself. And in the next slide, you can see the results. And here we chose three algorithms. First is Impala, and Impala is based on PPO, and it's a distributed algorithm, so it performs really well in vectorized environment. And we chose vectorized environment for Isaac tasks. And vectorized basically means that you have multiple environments. In our case, it was 4096. And for each environment, a single agent is performing all the tasks. And here, Impala is the most advanced algorithm. It's performing well in the distributed environment, and it's outperforming PPO. Second is PPO, which is also performing really well. And in general, PPO performs in a very dense reward type of environment. And finally, we have SARC, which uh, it, it doesn't perform well, and we consider it to be a failure. And overall, SARC is known to perform better in a more sparse environment and not in a dense environment, dense reward environment situation that we are using for our tasks. So these are the results. And next, we have another experiment, and this is a mobile manipulation experiment. So here, this is more of a problem-solving type of environment. So we have a robot and we have a trained agent that we trained on picking task. And in the video, you can see the user gives an input to the robot. So basically, for example, the user can ask the robot, go pick up an apple. And then the robot basically starts the navigation phase. So here only the navigation controller is working and the robot is moving towards the object. And as soon as the robot reaches some threshold distance, in our case it's 0.5 meter, the manipulation controller starts working and the trained agent for manipulator basically performs the task, gives some action values, and the apple is picked up. And right now, we are not using an intelligent system for the navigation part. We are using a simple navigation controller and a straight trajectory. But for the manipulation task, we have the trained agent. And this is just a simple experiment just to see how well the trained agent can be used when the robot is not static. It's not a static manipulation task. And overall, the success rate is not it's not very impressive. It's only 68.2%, but it's possible to increase it, and we will discuss more about how we can improve the performance in a bit. So now we have some details about the future work that we will do. So first of all, we plan to use some knowledge map. And not basically how knowledge map works is we use the example of BBQ, and it's developed by our colleagues at MIPT. And here knowledge map utilizes the 3D scene graphs for open vocabulary object grounding. And then it allows the robot to basically identify and understand some diverse objects in an unstructured environment. And then by using this approach, by integrating this approach, the robot will no longer rely solely on the object data sets, and instead it can dynamically process and adapt to complex scenes using some semantic information or some contextual awareness, etc. And this can significantly increase the ability of the robot to perform context-sensitive tasks such as distinguishing between the different objects, for example. And next we have, one second, yeah. So next work includes intelligent mobile manipulation, because as I said, currently we are not using an intelligent system for the navigation part, but my teammates are already working on it. And here we have the example of the structure currently. So this is basically a joint level planning for manipulation and mobility, and combining the entire framework into a cohesive structure. And this will utilize a compressed scene representation extracted from the knowledge map that we discussed earlier. And also it will use some input like from an upper level planner. And by leveraging reinforcement learning, we can design a mobile manipulation policy that enables the coordination between the base and the manipulator. And some of the technical improvements that we can include here is advanced scene representation compression for making it more efficient, and more of a hierarchical RL structure that integrates the high-level planning and the low-level joint control for better coordination. And also we can opt for some seamless execution of tasks such as object manipulation while navigating in a dynamic environment. And this is very important for a robot like Aloha, which is supposed to work in a dynamic environment and in a household environment, and it needs to identify among different objects. So next we have sim to real, and this basically targets the deployment of the trained policy onto the real robot. And this is in our plans, and using simulator like Isaac Gym or Omni Isaac Gym, ENV, Isaac Lab, etc., we can create very high fidelity training environments as we have done already. and then these environments replicates the real world dynamics. So this basically reduces the gap between the simulation and the real robot. And here you have the example. As you can see, the robot is called Tiago, and this is done by the researchers at Stanford, if I remember correctly. And already the work has been done on sim to real and deploying RL policy on a real robot. And this is one of our next step in the future works. And finally, as we discussed earlier, the results for the simulations are pretty good, but they can be better. And there are multiple ways of doing that. We can try different type of training techniques like curriculum learning. We can try pre-training. We can try multi-agent systems. But the most interesting thing for us is the use of advanced reinforcement learning algorithms, specifically TDMPC2 that we discussed in the Mujoko part, which is a multitask algorithm, and it is supposed to be more robust and more advanced compared to PPO, which we are using currently. And we also have modem v3, and this is based on TDMPC1. So it's also a very robust algorithm, but it's not massively multitasking as compared to TDMPC2. And this algorithm has been tested on real robots, as you can see in the videos, and the results have been pretty good. So it would be very interesting to try either modem v2 or somehow modify TDMPC2 to test it first of all in Isaac Sim, and then via Sim to real, we would like to test it on a real robot. And finally, we have that would be the 1 second. So that would be the end of the technical part. And to conclude, we can say that adaptation of modern algorithms like TDMPC2 for autonomous robotics, for multi-control robots like Mobile-Aloha, which has base and manipulator. It would be interesting to see algorithms like TDMPC2, which are multitasking. So we could use a single algorithm for single agent for the entire structure. We won't have to like divide it into different agents. And this would solve a lot of problems with data, with the complexity of training agents, etc. So this is really interesting. And secondly, as I said, multitask algorithms like Dreamer v3 and TDMPC2 can be employed for training, but at the same time, since TDMPC2 is a fairly new algorithm, it hasn't been tested on a real robot, and it might have some technical issues, but that's the thing that we want to work on. And also the adaptation of advanced RL algorithms for uh, realistic robots needs to be studied more. And from the results, we can see even though we have some state-of-the-art single task algorithms like PPO, state-of-the-art or multitask algorithms like Dreamer v3, even in simulations, they are not very robust in high complexity environments. So it can be even more problematic if we try to use this algorithm in a real robot. So these are some of the drawbacks, some of the conclusions that we can draw from our research. And as you saw in our future works, we are working on these drawbacks to fix these problems, and hopefully we will have some really good results on it soon. So that would be the end of my presentation, and our research was supported by SBARE Robotics Lab, and I would like to thank them for the support also. And that would be the end of my presentation. If you have any questions, feel free to ask.
Да, спасибо большое, Aditya. Thank you very much for your presentation. I think we can ask in Russian and English, and you of course can answer in English. Окей, какие у нас вопросы, Дмитрий Александрович?
Thank you, Aditya. Could you, maybe I missed this topic in your report, but could you please explain again what is multitasking RL agent? What is the difference between multitasking and single tasking RL agent?
So as I discussed in my report, I'll try to find the exact slide. Yeah, so as I already said in my presentation that single task RL agents are basically agents which can be effectively trained to do only one task. So for example, if we have two different tasks, one is picking up an object and other is navigation. And in case of single task algorithms like PPO, the agent can be trained to do either picking up of the object or navigation. And we can try training it for both, but the results would be really bad, especially its architecture is not suitable for different type of, for example, action space, etc. So this is the single task agent. And then we have multitask agents like TDMPC2. And these agents can be effectively trained to do different type of tasks. So for example, we have the picking task, we have the placing task, we have the pick and place task, we have the navigation task, etc.
Okay, thank you. And maybe another question, why TDMPC is not implemented in real robot, for real robot yet? How do you think?
So basically, TDMPC2 is a pretty new algorithm. It's pretty novel algorithm. So first of all, there hasn't been enough time to implement it on a real world scenario. And secondly, it's a very complicated algorithm, and there aren't much of an example of using it, and even in Isaac Sim, which is really necessary if we want to deploy some trained policy in a real robot. And even in our current work, we have had some problems with the way TDMPC itself works because it's also off policy like sucks, so its performance is not as well in a vectorized environment, which is one of its drawbacks. And also, it's like the entire architecture of TDMPC2, it's based on neural network. And we saw that there are in total 6 neural networks for TDMPC2 as compared to Dreamer v3, which has only 2 neural networks. So the entire thing makes it very complicated to adapt it to a real world scenario.
Thank you.
I
Yes,
also have a
thank you very much
question.
for question. Dima, да, у тебя есть вопрос?
Can I?
Мгм.
Thank you,
Давай.
thank you. Aditya, thank you for your presentation. And I want to ask a question about reliability of your approach or this approach that you listed in this table. If you want to transfer your model from simulation case to real robot, you need to have you need to show that your manipulator not be broken, because these models allows errors during learning with simulator, but in real case you can't have errors, but you of course may have errors, but your robot must be okay, and it can be broken in this case. What do you think about this maybe algorithms of secure control, of safety control, when you want to transfer your these policies to real robot?
Thank you for the question. It's a really good question, actually. And of course, there have been policies, for example, like Modem V2 that we discussed, which have been they have been deployed for a real robot. And in case of, for example, TDMPC2, this is one of the drawback because we need to, first of all, encode the actions and the observations in a way that the agent would be able to perform various tasks safely. So that's where, for example, knowledge map comes in so that the agent is able to get some additional information about the environment that it's supposed to work in. We can add some planning using maybe MPC itself for the joint trajectory, etc. So of course there needs to be work done, and also we discussed about sim to real, which is already being used for deploying RL policy on a real robot. So in this case, we train the RL policy in simulation and we get enough data so that we know that the policy itself is robust enough and safe enough that we can test it in a real scenario. So yeah, this is a very big topic, and this is a really big problem, a practical problem in the field of robotics in general, but we have a lot of solutions for it already.
And I also have another question about algorithms. How universal your algorithms for different robots. If you want to transfer or retrain or retrain again your policies for another manipulator, for example, you work with manipulator for Aloha robot, and if you want to receive similar metrics for example, your 5 robot, what you need to do for this transfer if you want to manipulate with the same objects?
Basically, our policies, they don't depend as much on the object itself as they depend on the manipulator, because UR5, if I'm not wrong, it has, I think, 6 degree of freedoms, and the Viper X manipulator that is being used in Aloha, it has 8 degree of freedom. So of course, we can't directly use the same policy for both of these manipulators. But what we can do is we can use the trained policy to generate more general data. And then we can use this data to train another policy, which would be much more faster because we already have the generated data. So in a sense, it's not as general as compared to, for example, if we are working on computer vision, as you can already know, that these policies, these data that we have for computer vision task LLM, they are more general because they don't really depend much on like where you are or what kind of robot you're using. But these policies that we use for the control systems, they really depend on the degree of freedoms that you have and how much each joint can move, etc. So they're not as general for different type of robots.
Thank you.
Окей, thank you very much. Так, ну что, есть у нас еще вопросы? У меня вот такой вопрос по поводу мультитаска и работы на различных типах роботов. Вот, Адитя, ты приводил пример потом Тиаго, робота, который вот хорошо подходит для задач различной мобильной манипуляции, но он двурукий. Вот, если ты обратил внимание, да, точно так же, как вот и Алоха, он двурукий, и те задачки, в основном, которые ты показывал, они на самом деле могут работать там с однорукой версией, да, а вот у Тиаго есть версия двурукая. Вот, как ты думаешь, вообще вот двурукость, она как-то будет сильно усложнять задачу? Можно ли, например, мультитаск распространить на манипуляцию одним манипулятором и двумя манипуляторами?
So it's a very interesting question, and I think one of the reasons of using multitask RL algorithms could be that like these algorithms are more general. So we can use, I guess we would have to use some kind of planning so that the agent itself is able to understand when it should use like bimanual manipulation, when it should use single manipulation, if I understand your question correctly. And in general, I believe that through the experiments that we have already seen, that multitask algorithms would be much better in these scenarios than single task algorithms because, of course, especially TDMPC2, as the action space increases, as the task gets more complicated, it's able to outperform the baselines. And this might be one of this might be the property of TDMPC2 itself, because it can be trained on doing different type of tasks in like a very big scenario, in a very big topic, very robustly without any particular hyperparameter training, for example. So I guess it's a really interesting thing to note, and yeah, it would be interesting to see how well they compare to each other.
Да, спасибо большое, Адитя. Так, ну что, коллеги, да, вроде все основные вопросы задали. Адитя, thank you very much for your talk. We wish you create a more advanced version of this algorithm and conduct experiment in Tiago for, I hope, in the future. Ну, а всем, кто у нас слушал, всем тоже спасибо большое за внимание. Присоединяйтесь к нашим будущим семинарам. До конца года у нас еще есть парочка тем для вас. Всем